The next person on stage is going to be Praveen. Praveen is from IIT Madras. I have no idea how he manages his day job as the CEO, founder, and president of Mobility Vision. He has not had any sleep for I don't know how many months, putting together all the back-end stuff for this conference. Many people in the audience, as I've been walking around, have been telling me that every year the conference gets smoother and smoother. You don't see any of the hiccups. You know, it just gets, everything just works like clockwork. A lot of that is because Praveen has been spending a lot of sleepless nights talking to sponsors and speakers and startups, helping put this conference together. So please give a warm round of applause to Praveen.
I'm going to my next duty before bringing to the big key person in the world who started talking about AI and doing research and innovations way back when the AI term is there. It's none other than Professor Anima. And I'm sure you don't need an introduction anymore. You are like multi-talented, multifaceted in any ways, and whatever, you know, cultural or like technology, innovation, or research, or whatever it may be. You name it, you can see Anima over there. First and foremost thing I want to again mention you that when we started planning for this conference this year, the first speaker we reached out to was Anima, and within no minute, Anima accepted that invitation. So big thank you for that one, and huge success for this conference. The other thing is that we both share the same campus, IIT Madras. It's a far difference, decade difference, but still, that's what we were chatting on, how the campus have been changed over time. So without much ado, can we welcome Anima? Anima.
Thank you.
Thank you.
Thank you.
So the green is the forward.
Yes. Yeah. Thank you. It's such a pleasure to be back here. I think we were just reminiscing that I was at the same event maybe a decade ago, and after that we had a dance party. So it just bringing the community together is what I really treasure about being part of the IIT conference here. And also just, I was back at IIT Madras last year, so it's great to see that growth there. A number of startups I spoke with there, as well as, right, everything is expanding. So that was great to see as well. I think even in this age of AI, it's very important to have these human connections. So as I delve into all those technological breakthroughs and all of the exciting developments, we should not lose track of the fact that being connected, bringing everyone together, and enabling us to make that next leap in innovation, that is really important. And so we as a community here in Bay Area and in the broader tech sector, it's important to not only harness what AI is doing today, but also enable that next wave of innovations. And when I was at NVIDIA, I was able to see that full stack, right? So my background is electrical engineering in IIT Madras, but I pivoted very early to machine learning and signal processing way before it was as cool or as practical as it is today. But starting from that theoretical development to going to Amazon Web Services and then NVIDIA, seeing that really turn into products, right? And seeing that with a full stack view all the way from hardware efficiency to developing new algorithms, all this has to come together so we're no longer bound by the traditional confines of disciplines, right? Am I a computer scientist? Am I an electrical engineer? Am I a physicist? I may not be an expert in every one of these areas, but at CalTech, what I really treasure is this interdisciplinary approach to doing AI. And that's how many of the developments that you'll see is both developing AI, but also harnessing it to make new scientific inventions and discoveries. What if we could do better medicinal drugs, better medicinal devices, be able to design better aircrafts and rockets? What role does AI play there, right? How do we go from traditional engineering, something that I grew up with since my parents are engineers and had CNC machines. So coming from that perspective and asking how AI could improve those design cycles, help with R&D cycles become much faster and better, and really usher in the new era of science and engineering as well, in addition to just the pure software world that we are accustomed to. So we're able to ask all of these hard and bold questions because of the power of what AI can do today. Yeah, so before I go into what the future holds for us, let me just quickly recap where we are today. I mean, we are in this era of generative AI, right? So popularly, think of them as language models, but it's much more general than that. What's really happening is you start giving certain specifications or prompts, and you're able to generate entirely new pieces of text, new images, new videos, but also new drug molecules, new enzymes. So it's not just limited to text. And I think that's something you want to be mindful of. This concept of generative AI is much broader than just generating text, right? But that's a great example. And the other aspect that a lot of people were surprised when this became very practical and ChatGPT was released is the fact that the training objective is so simple, right? So you're training just to predict the next word. And so that seems not enough to go and generate new pieces of text, really understand the meaning of what the prompt is saying. But it turns out this plus what we call instruction following or reinforcement learning with human feedback is very similar to what a dog does. Like dog changes its behavior. If you ever have a dog or interact with a dog, you know that it can be trained with treats. At least many of the dogs can be trained with treats to follow instructions. And in a way, it's very similar that the language models can be then aligned to what humans like. And that's also a very deep question, right? What is the right alignment? Do we align it for factual information, or because humans just want the language model to agree with them? Is that the right thing? So there are ethical and other social questions as well, if you really go deep into how to achieve this alignment. And that's why there's a lot of interdisciplinary research on how to get the right alignment if you're serving these products at scale to billions of people. But then it's not just language models interacting with humans. You can have language models interact with each other and recursively get better at certain tasks. So this is what we call Mind Dojo. This is Minecraft playing agent. We released almost immediately after ChatGPT came out. And what was surprising to a lot of people was how it can now play these Minecraft games. Of course, now you have many world models that are interacting and playing with AI agents. And we also have all kinds of agents doing tasks like answering customers, right, filling up web queries, so on. But the concept is the same, that you can use language models in repeated interaction fashion to do certain tasks. And then that doesn't have to be limited just to the digital world. We can go to the physical world, and now we are also in this golden era of robotics, of how we can have what we call embodiment, right? Because the mind has to be together with the body. And so far, robotics, until this present era, had advanced a lot, but it wasn't learnable. So you pre-programmed it to do car manufacturing, or even I've seen those machines with robotic arms, but they were very rigid, and they couldn't do anything else other than just what it was programmed for. On the other hand, we can have now robots learn all kinds of instructions, and you can make it textual instructions, you can talk to the robot, you can even do gestures. So all of this is now being researched on how we can have robots that continuously interact with us, they're safe, they're able to adapt to doing new tasks, and I think that's where language models enables the instruction aspect of it, but you also need to take care of the physics, which I'll show you in a bit later, because if you're going beyond just manipulation, and even there, but especially if you have, like, say, drones flying in unsafe, high wind conditions, you also can't ignore physics, right? It has to understand the physics internally to be able to do that. So language is a great way to give instructions, but it also needs physics to deal with the physical world. And so when we're talking about text, I mean, it's not only just English language, we can also ask it to do mathematical reasoning, and in fact, we think of this as the pinnacle of AGI, right? Whether you believe in artificial general intelligence or not, I think everyone agrees that trying to prove mathematical theorems, especially those that are still conjectures and unsolved, would mean that it's an intelligence that is even more superior than humans. And we are not at there, right? We are not at there where AI is able to prove unsolved theorems, but on the other hand, it's able to solve high school math Olympiad. I don't know if any of you attempted that. Of course, the JEE exam back then had a similar, if not the same level. So, we know how much of a deep logical reasoning is necessary to solve those problems, so that's very promising. But one thing that's still lacking if you directly use these language models is verification, right? I mean, don't worry about the details of what I've shown as an example theorem, but what it is a tree. You go step by step, and if you're claiming that this is my next step in the proof, you need to verify it's correct or not, right? You can't just say, I've proven this, I'm done. There has to be verification. And so this is going back to like formal programming. If you did computer science, you would have come across software and formal programming, right? But then this is useful even in the AI era because you can now verify every statement that language model makes. So you can combine formal programming with AI together to have completely hallucination-free AI. Meaning you can trust the AI 100% that everything it says is correct because it's verified. Of course, it may just get stuck and say, I don't know how to prove this theorem or do this software programming beyond, I can't complete the program, but then at least it won't give you something false. And this will be very crucial for all kinds of applications. If you're putting a software program and it goes to Mars, in JPL, at NASA JPL, we have people working on that. You can't afford to have it make mistakes, right? I mean, cybersecurity, blockchain, so many of, like software, if you can make it completely bug-free and you know the behavior, it can be very powerful. And so AI is going to make an even bigger revolution when it comes to software programming, because eventually we'll have all software programs that are fully verified, meaning you know that it's bug-free and you know that it cannot be hacked. And so I think that's a very exciting future to have. And as I said, we have the first open source framework where we combine language models with these formal programs like Lean. And so that way we can conduct research and test how good do these language models do, and at the same time have the verification aspect. And in fact, just yesterday we submitted a paper where AI is now able to come up with new progress on open mathematical conjecture. So not just high school math, but really something that the humans haven't been able to solve. And we've made progress. We haven't fully solved it, but we've done much more progress than what was known before. And so that's very promising that AI is really getting to the frontier of what is the knowledge today, what isn't possible today. Yeah, so I talked about AI as mostly language models until now. But of course, there's a bigger world out there with all kinds of data beyond just text, right? And that's what, for science, there's so much AI can do. And so one of the projects we did in the height of COVID was to ask, can we understand how coronavirus evolves? If we could predict the mutations before they happen, then we can have vaccines and we can be ready. We can, of course, have better also drugs, antivirals, everything to help the population. And so, at that point, of course, we could try and map, there is the alpha and beta variants, how do I know what's the next one going to be? But instead, we took a foundational model approach, meaning the same way that language models were trained on all of the internet text, we asked ourselves, let's look at the genomes of all known virus and bacteria. So not just coronavirus, the flu virus, E. coli, whatever, everything that the humanity has already recorded in the biobank as viral and bacterial genomes. And why is this useful? Because in the past, right, all of these flu, E. coli, all these virus and bacteria have also evolved, they've mutated. So if you could understand their mutation cycle, their evolution, and then use that information to predict how coronavirus evolves, then that can be very helpful. And instead of us humans trying to understand manually one by one, which is impossible, we just gave this about few 100 million genomes to the language model, meaning instead of like text, we are training it now on these genomic sequences with the same principle. And then we wanted to ask, can you predict what new virus mutations will be? And we were able to do this. I mean, this is just showing the layer or latent space of this genome model. And it's able to cluster not only the known variants like alpha and beta variants of coronavirus, but also the ones like Delta, Omicron, and even the ones that came much later. So it was able to predict that beforehand. So we can be prepared to have this for the next pandemic. And not only that, we've used the same model not only for virus and bacteria, but also for designing new protein enzymes. Because the same principle, right, of biology, which is happening at the genome scale, is also applicable to designing new functional enzymes. So in Francis Arnold's group, who's the Nobel Prize winner at CalTech, we were able to come up with new functional enzymes with this AI model that 2 decades of research in the wet lab hadn't shown. So that's the power of AI. It can really go to new parts of the design space that no human has gone before, because we are limited by the experiments we can do. We are limited by the knowledge in the vast array of proteins. There's only a few we've so far experimented with. And with AI and careful filtering of what AI tells us, we can go and glean at entirely new drugs, new catalysts that will really revolutionize all different sectors. And so that's where I talk about this need of physical understanding, right? So if you really want to understand physical world and make an impact on science, you want to start from the atomic level, of course, understand proteins if you want to design better drug targets. And then you want to go to even planetary scales, like being able to predict weather, being able to forecast what kind of climate change will happen if we have increasing carbon dioxide. So all of this requires understanding of the physical world. And that's where language models cannot do this. Language models have a high-level understanding. It can tell you all the theory behind quantum mechanics, right? But what it cannot do is fully simulate an entirely new molecule and say, will this be a better superconductor, for example? And so that's where we need AI that's trained on the data that comes from the physical world. It could come from atomic level energies. It could come from, say, wind, and humidity on all kinds of variables for weather prediction at the planetary scales. And with training AI on that kind of data, you usher in a new era of AI-based scientific modeling, inventions, and discoveries. And so to give you an example, we were able to train AI to do quantum chemistry better. So, and this is, in fact, used in drugs that were discovered that are now in clinical trials. And so you really see the power in which AI can quickly design drugs, and we can get them faster to clinical trials. We also used AI to understand how viruses like coronavirus spread in the air, and doing the calculations at the atomic level means we can have very precise calculations on how infectious it is. And so this is just a visualization of that. Like you really have to zoom in into several scales, right? So you go to these atomic scales, that's the coronavirus. It has the spike protein, which is in blue here. And then you want to look at how the protein structure here in the spike protein affects how infectious it is if somebody coughs. And these calcium ions in our respiratory aerosol, they bind with the spike protein, and that strength tells us how infectious it is. And so we are able to do these simulations and speed them up with AI. If you did that without AI, it's just not feasible because it's too complicated. And AI speeds this up by thousands of times to make it simulations that were not possible before possible. And that also happens when it comes to planetary scales, right? So as I mentioned, in order to precisely do weather and climate modeling, you need to go to fine resolutions to get all the details. For instance, if I want to look at where a hurricane is going, the resolution matters, meaning the more information you have near the hurricane, the better you will be to predict this. Of course, we cannot afford to have all of the satellites just for one hurricane, right? There is physical constraints. And then you can look at the laws of physics itself. So it's not just the satellite data, but I know some fundamental laws of physics. For instance, Navier-Stokes tells me how the fluid moves and what is the turbulence there. And so you combine data and physics together, and then you can do much better than what you could with traditional simulations. And that's where we developed a framework called neural operators that expand standard neural networks like transformers that were used in language modeling to now continuous spaces. Meaning the example here is if you have a fixed number of pixels, which standard neural networks do, even if you zoom in, it gets blurry, right? There's no further detail. Whereas on the other hand, neural operators can zoom into any level of detail. And so you can keep zooming in, and you can capture more of the accurate physics to come up with predictions that overall are accurate. And to give you an example, we built the first high-resolution AI-based weather model called ForecastNet. And to our surprise, it was not only accurate, like you can see it predict the atmospheric rivers, which really affect here in California, whether we have drought, whether we have lots of rainfall. So being able to do these long-range predictions that are thousands of miles, but not only that, do that much faster than what's possible with current traditional forecasting. So tens of thousands of times faster. So what would require a supercomputer to do weather forecasting can now be done in your home. So if you have a gaming GPU, you have a desktop, you can run these weather models. So it's miniaturizing what AI can do for science because it's so much cheaper and faster. And it surprisingly not only does well on typical weather events, like being sunny in California, it's not so surprising if AI predicts that well, but also extreme weather events like hurricanes. As you can see here in orange, our ForecastNet, the AI model, was able to predict Hurricane Lee several days in advance before traditional weather models were able to do and do that accurately. So it's making a big difference in our ability to handle catastrophic events, right? If you could give early warning, that's really essential for people to evacuate, to plan, and so on. And it's available in the premier weather agency, ECMWF, so it's online. Anybody can go check this out. It's been online for more than 2 years now. And that's where weather scientists got a lot more confidence, right? Because this is not just overhyped AI, it works. And they see side by side, what is the weather prediction from traditional physics-based computing with no AI, and what is AI telling me? And that's where they saw that AI can even do better than before and faster. So there's no trade-off, right? It's a winner on all fronts. And that's really changed how people now invest for weather and climate and all of these natural disasters with AI. And there's been now a project even of predicting monsoons in India with these AI-based weather models. So I think this is going to touch lives, especially people who are not able to handle the impact of climate change in the developing world, in the global south. I think this is very important that we enable everybody with early information to deal with extreme weather events. And part of that means also better risk assessment. Of course, here in California, in LA, I was close to CalTech, so that, thankfully our place was fine, but many of my colleagues lost their homes. So wildfire risk is a hard one. So we have not only thinking about, okay, can we immediately do weather prediction correct, but long-term risks, right? So we need to be able to handle the risk assessment correctly. And what AI can do, I showed here the example in the hurricane, how you can do lots of different runs. So you scenario plan, you add noise, and you look at where the hurricane goes. And you can do lots of such scenario planning because AI-based weather models are so cheap, right? If they're tens of thousands of times cheaper, you can run it in a small GPU. You can do a lot better risk assessment. And that's not only true for weather events, but also climate events, like long-term climate change. It's, here in California, it's so important that we plan better. We plan better for insurance risk. We plan better where to build. And these models are very important in enabling us to do that. And so speaking of climate change, even technologies like carbon sequestration. How much carbon dioxide can I pump underground into reservoirs? And will there be pressure buildup, right? Where will the carbon dioxide move? Again, there's not going to be one overarching solution to climate change. There will be many. And what AI is enabling is allowing us to do in simulation this kind of planning. Is this the right solution? Right? I'm not the expert. I'm not going to answer that question. But what I'm enabling the experts is giving them these AI tools that really, they can do a lot more simulation. It's much cheaper than going and building a physical plant for carbon sequestration. And so this is being used in Shell, Exxon, and many of the energy providers to study carbon sequestration. And of course, we are looking futuristic as well and asking, what about new sources of energy, like nuclear fusion? So this is the picture of the tokamak in the UK. And what you see here is, as the plasma heats up, it can go disrupt, right? It can go haywire and damage the reactor. So that's one of the single most bottleneck or a barrier to making nuclear fusion practical. And so what we are able to do with AI is be able to predict these disruptions accurately and do that 1 million times faster than what was possible earlier with accurate physics-based simulation. But we have the same accuracy, but we're 1 million times faster. And so we can now understand the complexity of phenomena like plasma and one day, hopefully, come up with nuclear fusion that is practical. And we're doing all kinds of different designs. We have this other Stellarator project, which is like a donut-shaped thing. So it's a very wacky design, and it's based on magnetic field only. And people thought it was impractical, but now with better magnets, it's getting practical. And we are now developing AI and asking, can you design better magnets? Can you design better shape of these reactors? And so it's so much better if you can explore that whole design space rather than deciding to put billions of dollars to build these reactors, right? And then saying, oh, this wasn't the optimal design. And so that's where AI can enable us to capture the physical world in a digital realm, optimize design, do all the modeling, right? Really explore extensively there before going back to the physical world. And you see that also with the ability to design drones under extreme wind conditions. At CalTech, we have these array of fans, and it can simulate very high-speed winds, like 90 miles, 100 miles per hour wind. The LA wildfire did have those wind speeds, right? And the reason why it was so destructive is we couldn't have any helicopters, aircrafts fly and put down the fire. And they could only fly after the wind died down. And so if you could have drones and unmanned aircrafts that could really fly in extreme conditions, that would have been game-changing. And so for future wildfires, it's important to think about pushing this boundary of what is safely possible today with flights. And we have birds being able to fly in these conditions. So it's possible, it's just the current design is too rigid to enable. And so to enable future designs, how can we have AI understand the principles of fluid dynamics, have sensors that can predict how, that can both observe and then you predict how the wind turbulence will change and be able to handle these extreme conditions. So this aspect of understanding the physical principles like fluid dynamics is also powerful in being able to design better medical devices. For instance, one of the biggest source of healthcare-related infections in hospitals is the use of medical catheters where bacteria can swim upstream, infect the human. And what we did was a simple principle from fluid dynamics where we designed triangular grooves, and we were able to optimize the design. Again, AI can extensively explore the design space, and we 3D printed, and this is the actual bacteria under the microscope. And what you see is they are being pushed out, and they're not able to swim against the fluid flow. And so this is where we were able to measure a 100-fold reduction in bacterial contamination. So AI-optimized design can really work in the physical world if you can put in the right principles of fluid dynamics and physics and make sure that what it's designing is going to be accurate. Yeah, so to conclude, I hope I gave you an overview of where AI is today, but also where AI is heading in future. While language models are having a big impact in all of us being able to access and have better information, do better research, we're also seeing AI for the physical world, AI and science coming together. So, like the engineering principles with which we grew up in IIT, I'm really happy to put that together with AI to design AI for the physical world. Thank you.
Thank you, Anima. Thank you so much for the wonderful talk. Since Anima needs to rush to the airport, we don't have opportunity to have a QA session. But I do have Manya over here, who is a first-year undergrad at UC Berkeley, going to have a very quick interaction with Anima, her journey, where she is now. Manya?
So you talked so much about how interesting the software is opening up so many capabilities for climate change research in the medical field.
Yeah.
But I thought it was really interesting how you talked about how there's so much potential in the embodiment for robotics. Yeah. But since it's so hard to disseminate the technology with the mixture of hardware and software with so many iterations, what do you think it will look like in the future, disseminating these technologies in the home to bring ease in daily life?
Yeah, absolutely. I mean, to me, a lot of the software development over the last few decades has meant that the engineering hasn't progressed to the same extent, right? If you think of robotic hardware, it's the robotic form. And in fact, there was a nice essay by Rodney Brooks, he's the, you could call him a godfather of robotics, who, he's you can't just rely on software. For instance, for dexterity, you need touch, right? You need touch sensors. You need like that ability to have that feedback. Yeah. And if you have very rigid, like looking things that like the the holders right now, if you see in robotics, you cannot get to human level dexterity. So, and that aspect of design, you can also bring in AI. So, I talked about AI being able to come up with better design shapes, better materials, better semiconductors. So, all of this design too, we now have more freedom to explore than ever before because it gets very quick to prototype and try different options.
I see. So like making hardware like have the dexterity in order to take in the iterations in the software.
Yeah.
Hey, thank you so much. That was my only question. Thank you so much, everyone.
Yeah.
Thank you, Manya. Send me.
Thank you, Anima.
Thank you.
That was a very informative session.
Thank you.
And in the audience, people were just wowed by your breadth of experience. Such a great example of straddling academia and industry, and you were like speaking without a pause. We loved it. Thank you very, very much.
Thank you.